One I like to show is a beryllium copper, because we're seeing more and more beryllium copper in these recycling facilities, and with X-ray you can't measure beryllium, so it's very hard to find that. So as an example of how quick and easy libs can be, there's a common beryllium copper. We'll shoot it, a couple of seconds, see it comes up, and there's your beryllium reading around 2%, which for this alloy is pretty typical. So that's a real benefit right there. You can measure an element that previously was not able to be measured with your other handheld device. Another big area that you pick up speed and sorting and material processing on these copper alloys is your aluminum bronzes and your silicon bronzes. And that's because, again, LIBS measures the aluminum and the silicon very quickly compared to X-ray. So take a typical aluminum bronze, and you'll see in just a couple of seconds the aluminum ring comes up. It identifies it as 863, which is what it is, around 5 or 6% aluminum, so a little bit of silicon. So there's your aluminum bronze. Very, very quick reading, just in a couple of seconds. Another good example of your silicon bronzes. So this one, again, a few seconds. 655 is the alloy, about 2.5–3% silicon. So these silicon and aluminum bronzes, along with your beryllium coppers, can be very quickly sorted and identified. Another one I like to show, because it's quite specific to this analyzer, is a lot of these enviro-friendly brasses. These are the brasses that now include either selenium or bismuth or both instead of lead typically. And the thing that's good to point out with this is you need a spectrometer. The best selenium lines are down around 190 to 193 or so nanometers. Those are the best selenium lines to use. So if the LIBS analyzer you're using really has to have a spectrometer that goes down to about 190 nanometers. And this is one of the few, perhaps the only one, that goes that low. And you need argon to really get down there and do a good measurement, because those good selenium lines are down there. As you can see, that was a few seconds test, and you can see the 1% or so selenium that was picked up. Let's start out with a very common refinery alloy. Here's 1 1/4 chrome. Pull the trigger a couple of seconds, you get your 1 1/4 chrome. And you see it's a nice chrome result, about 1.2%, which is typical. Something worth pointing out is, and the moly as well, down around 0.5%. For a lot of LIBS units, measuring low concentrations of moly is very difficult. Moly is a very refractory element, and exciting it into the plasma is hard. That's where the powerful laser, the good spectrometer, and the argon all help. So as you can see from that, we can very quickly measure that 0.5% or so moly. That's critical to measure in this refinery alloy, this 1 1/4 chrome. Another good example is a low alloy steel. Pull the trigger, wait a couple of seconds, and I'm going to let this run out the full 5 seconds because I want to make a point about some repeatability. It's one test. Next test. And then let's do one more test. And then the thing to show is looking at the chemistry of these. So I want to focus on titanium, vanadium, some chrome. So test 1, about 0.3% ti, about 0.3 vanadium, about 0.25 chrome, nickel about 0.46, moly about 0.52. So try to remember those numbers as we swipe back to the last test. Ti again was 0.3, vanadium 0.28 instead of 0.3, so very good repeatability there. Chrome 0.32, let's go back, 0.32, 0.25. Let's look at nickel, nickel 0.5, and here 0.46, again a good repeatability, and then moly 0.52 in the first test, again 0.52 in the next test, and then that third test moly was 0.50. So it's really good repeatability on moly, and vanadium as well, 0.33, 0.28, and 0.3. So very good repeatability. I like to point out the vanadium repeatability because there's a very important petrochemical alloy called P91, which is a 9 chrome, very common, except it's got about 0.2% vanadium in there. So we have good vanadium repeatability, and so measuring that P91 versus that 9 chrome, which is a very important measurement in the power plants and the refineries, can be done quite easily. Let's move on to a couple of titaniums. One I like to show is not such a common tie alloy. It's 325. Will come up in a second here. But it's 3% aluminum, 2.5, around 2.5 vanadium. That's an important one because a good LIBS unit needs to be able to distinguish the 325 tie alloy from the very common 6.4 tie alloy, which is 6 aluminum, 4 vanadium. And this one does that very well, as you can see. Another thing I like to show, and this really goes out to a lot of the titanium sorting equipment that's used. Historically, a lot of tie alloys have been sorted with arc-based spectrometry. And one of the well-known, I don't know, not weaknesses, but one of the well-known issues with that kind of sorting is the tie 6242 and tie 6246. They only differ by the 2% versus the 6% molybdenum in those two tie alloys. And some of those arc-based sorting techniques can't separate 2% moly from 6% moly because in that technique the moly line saturates. But I just wanted to show that very quickly. So with LIBS, you don't have that problem. You can easily measure that moly. This is a 6242 as it comes up. So you see the moly is about 1.8%. Now let's shoot our 6246. Measure 6246, again up around 6% moly. So that's a very, very fast, quick separation on two alloys that have historically been hard to separate with some of the optical emission techniques that are used in the industry. Again, the powerful tube and the powerful laser and the better spectrometry. In a few seconds, you get your waspaloy, which is a very common nickel cobalt alloy. Let's pick out some other ones. See what this guy is. My old X-ray days keep coming back when I say tube instead of laser. That one's a 625. No surprise there. Astelloy X, again. So as you can see, we can kind of run through all these nickel alloys fairly quickly, get a good chemistry, good ID. There's your C4. Another common one, 718. 718. So, as you can see, again, so X-ray is really a very well-established technique for nickel alloys, but what we tell our customers is with the LIBS with the argon will do a good job on your nickels. So you can use it for those. You can use it as a backup if you don't have a lot of aluminum or red metals or tie alloys to sort that day. The last thing I want to show for some nickel alloys is, again, with the argon, the repeatability you can get even on nickel and some of these nickel cobalt and super alloys. So I'm going to shoot this waspaloy 3 times. Do three quick shots. Another one. These are running about 4 to 5 second tests, which is about the longest test time you'd ever need for the laser. I think these are probably some of the most complicated alloys that you're going to run into, especially for LIBS. One other thing I like to point out is that the aluminum measurement and is very quick. There's a lot of several percent aluminum in a lot of these nickel alloys, and you see that right away with the libs, where you don't with the X-ray. You need the dual beam test. So that was the 3 waspable readings. And if you look at the repeatability, let's just focus on nickel. Last 3 readings: 56.1%, 56.4%, 55.3%, and consider the cobalt: 15.4, 14.5, 14.9. So, and the nickel is like plus or minus about 0.3, 0.4% maybe. Cobalt a little bit higher than that, but that's all right. So that's pretty good for a 4 or 5 second test on a laser-based unit. A lot of libs companies will tell you that you should only use libs for aluminum alloys. That's probably true if you don't have an argon supply and a powerful laser, but this unit with those 2 features, you can really do the full gamut of these alloys. And let's do an even harder one. This is one of my favorite super alloys. It's CMSX4. It's got some tantalum, some rhenium, some tungsten, some hafnium. So we'll shoot that 3 times as well. Okay, so you get the quick ID CMSX-4. Let's let it run the full 5 second test. Hit it again. CMSX4 again, as expected. We'll hit it one more time, and we'll swipe through and look at some of the results. CMSX4, so good, 3 solid good IDs, very repeatable. And then the thing I like to point out about this is, let's look at scroll down a bit. Tantalum 7.7, tungsten 4.5, rhenium 4.5. That's 1 reading. Let's just focus on those 3. Tantalum 8.4, tungsten 4.3 versus, what was it before? 4.6. Very good. Rhenium was 4.5, 4.2. Then the 3rd test back. Go down. Tungsten 4.27, rhenium 4.0. So again, and though tungsten, tantalum, and rhenium are really probably the hardest alloys to measure with libs. And with the argon and the spectrometer and the laser, even those we can do with this. So we have customers testing the super alloys with our handheld libs, and it's working quite well for that.